These will be the homework solutions for Chapter 5.3, textbook homework problems. We're going to start with number 11, and keep in mind for Chapter 5.3, we go to new types of probability problems. These problems involve what's called the multiplication rule. Multiplication rule for independent events, and then we have the multiplication rule for more than two independent events. And so you can see it involves a situation where it's and. What's the probability of this and this happening? You might hear me also say this is a sequence of events problem, like when something happens one right after the other, and when those events are independent, meaning that if you go back to your notes on this one, two events are independent if the occurrence of one event does not affect the probability of another event. So again, that's the idea of independence. You'd want to go back to your notes and take a look at that definition in Chapter 5.3. In the definition of Chapter 5.3, you would want to highlight that aspect. That one, where is it? Two events are dependent. It's right here. Oh, 5.4. Looking at 5.3 right here. Two events are independent if the occurrence of an event does not affect the probability of another event, right? Two events are dependent if it does affect the probability. And so in these examples, we talked about things that were independent and independent or dependent. So let's go ahead and look at the solutions. Starting with 5.3, number 11. What is the probability of obtaining 5 heads in a row when flipping a fair coin? So in this problem, what we're looking at is the probability basically of flipping, you getting a heads and a head, continue on, right? And a head 5 times. And so that looks like this form here. It's a sequence of events, ahead, ahead, ahead. The probability of each of those, the probability of getting ahead is 1/2. And so what we would, to solve that, it just becomes the product of 1/2 5 times, or you may see us use exponents in this case. And so the answer in this problem is 1/2 to the power of 5. That's 1/32. And then if you want a decimal answer for that, you get 0.03125. So that would be unusual to get 5 heads in a row. That's number 11. Moving on to number 12. What is the probability of obtaining 4 ones in a row when rolling a fair 6-sided die? Interpret this as a probability. And again, interpret this probability. This would be unusual because it's less than 5%. And so again, from our definition, something's unusual if it has a less than 5% chance of happening. What is the probability of obtaining 4 ones? So the probability of getting a 1 when rolling a die is 1 out of 6. The probability of getting a 1 and a 1 and a 1 and a 1 would be the probability, basically, because these are all, again, independent events. It doesn't, when you roll a die, it doesn't remember what happened last time. It doesn't affect the probability, so this should be 1/6 to the power of 4. So that answer would be 0.0008. So again, this is very unusual. Number 12. 13 gets a little bit more complicated. So let's take a look here. The LISA is a test to determine whether HIV antibody is present. test is 99.5% effective. So we will, at some point, I'm pretty sure, have to convert that to a decimal to use, which means the test will come back negative if the antibody is not present 99.5% of the time. The probability of a test coming back positive when the antibody is not present is a false positive, and so that you can see a value there. And so just because you take a test and it says you test positive doesn't mean you actually have the virus, and that's what it's saying here, or in this case HIV. Suppose that the ELISA test is given to 5 randomly selected people who do not have HIV antibody. What is the probability that the ELISA comes back negative for all 5 people? And so in this case, it's effective if it says negative. And so they're all negative, so in this case, it's probably negative for all 5, right? Negative for all 5. That's what we're looking for. It's the probability of negative for one person is going to be 0.995, given that they have that. And so in this case, your answer should be 0.995 multiplied together 5 times, or we would use the decimal, or just use a raised to the power to do that. And so in this case, you get an answer of 0.9752, or 3 decimals, 0.975. What is the probability that ELISA comes back positive for at least one of the 5 people? And so in this case, we need to get back to the definition. To answer this question, it's important to highlight what does at least one mean. And so going back to your notes here, you need to at least, or not at least one, but at least means something. At least means greater than or equal to. And so once we have that, so this, we can interpret that. What's the probability that comes back positive for at least one of the 5 people? So that's greater than or equal to one of the 5 people. And so think about how we would write that. We have to solve this in a creative way. So we have 2 ways to kind of think about this. The probability of at least one positive is really equal to the probability that one is positive, or 2 is positive, or 3 is positive, or 4 is positive, or 5 is positive. So we have to calculate each of those separately. What's the probability that at least one comes back positive, plus the probability that 2 comes back positive? Those are positive signs. Plus that. So that's one way to do it, and that takes a long time. Another way would be to answer this would be at least one positive is equal to 1 minus the probability that none are positive. And so we calculate this none positive. None positive also is another way. If you think about it carefully, 1 minus the probability. None positive means they're all negative. And so to get this answer, there's a shortcut. We just kind of use this answer here, which was easy to calculate. And so it's 1 minus 0.9572. Again, at least one means greater than or equal to 1, 2, 3, 4. So this would take, we can do this. It just takes a long time. We think about at least one positive is the same as 1 minus the probability that none are positive. So we're using what's called the complement from 5.2. None positive is the same as all negative, which we've calculated. And so you get an answer of, on this case, you'll get an answer of 0.0248, which is again 1 minus that there. And so now to answer number 33 from 5.3, explain it. Suppose a mother already has 3 girls from 3 separate pregnancies. Does the fact that the mother already has 3 girls affect the likelihood of having a fourth? So basically what we're saying is, what's the probability that the fourth child is a girl? And so now you're saying, well, she's already has 3 girls. And so what's the probability that the child is a girl? And again, what we're assuming, the probability of a male is 1/2, probability of a female equals 1/2 at birth. And so in this case, her birth, technically, the fourth birth has, sorry, the first 3 births have no influence technically, unless she does her own testing or pays for it. But if she just has the child naturally, the probability of the fourth child is a girl is equal to 1/2, which means that the answer to this would be no, right? Does the fact that the mother already had 3 girls affect the likelihood of the fourth girl? The answer is no. These are independent events. And so that would be the reason why. That's it.